Today we'll talk about electric potential energy. And before we start working on the electric potential energy, I wanted to revise and remind you again of the gravitational potential energy. So if ground is somewhere in here, and you have an object that is at a certain height from the ground, then when you are moving up, when you are moving this object up in this direction here, then what is happening, the gravitational at A, gravitational potential energy is increased. And the reason that is increased, is gained, is because the work done on the object is against the gravitational potential field. Okay, so when you are moving the object in the opposite direction, so let's say that you're moving toward B, toward the ground, that as you are moving toward B, the gravitational potential energy is decreased. And you know that it's decreased because the height between the object and the ground, or that we consider a ground, is decreasing. And the gravitational potential energy formula is mgh, where m is mass of the object, g is the acceleration due to gravity, and height is the height of the object from what we consider as the ground. And as the object moves in the C or D position, so direction at C and D, there is no change on gravitational potential energy of the object, because the height of the object is not changing. So another way to see it is that you see what is the work done. Is if in this case here, when we have that the object is moving toward B, the work done by the gravitational field, the work is done by the gravitational field. Therefore, the gravitational potential energy of the object is decreased. When you are moving toward A, then the work done by is against on the object is against the gravitational potential energy potential field. So therefore, the gravitational potential energy of the object is increased. The same idea is when we have the object, the charges, okay, when we are talking about the electric potential energy. So let's suppose that we have a positive charge here, okay, and we have a point P that we are discussing. And let's say that at this point P, we are placing a positive charge as well. Okay, so now as you are moving toward the position, toward the charge A, or toward a source, toward the source, and in the A direction, then the work is against the electric field. Because remember what we said in terms of the electric field? The electric field for a positive charge is this one. The electric field configuration is this one here. Okay, So now as you are moving toward the positive source, then what is happening here is you are moving against the electric field that the source is creating. Therefore, at A, what is happening is that the electric potential energy is increased. Electric potential in the same idea as we did when the object was moving high up in the gravitational potential energy. It is against the gravitational potential field. Therefore, it is increased. And as the object is moving, as the charge on this case is moving in the B direction, so it is moving with the field, electric field, then on this case, electric potential energy is, guess what, decreased. It's the same as the position B that we had when we were moving an object toward the ground at the gravitational field. Now, as the object is moving, the charge is moving perpendicular to the field, which is a circle. So it's actually is a circle, but we can say that it's moving in this direction here, up or down. So it's a circle because this is a source point. The source point is a circle as well. So at C and D, then the electric potential energy is not changing. And as I said, like we are making it as a perpendicular, but actually it's if we are moving into a circle, because this is what is the electric potential energy is constant. Okay, so from this we can draw the conclusion that the electric potential energy is the energy of a charged object due to its position in the electric field, is the change of the energy of the object, of the charge in this case, due to its position in an electric field. Okay. Because now let's see what will happen if we have a negative charge. So the source is here, and then we have a positive charge here as well. So now the electric field configuration for the negative charge is this one. So what is happening here when we are moving charge on A position, so against, then the electric field, then the electric potential energy is increased. Okay, and as we are moving it in B position, then the electric potential is decreased. Okay, so just keep in mind that the electric potential energy is as a result of the position, is the change of the position of the object due to the relation that this object has in an electric field. So now the electric potential energy is known as the voltage, and it's the difference between the 2 points that you are comparing it, because even when we are talking here, we are saying that the object is moving towards, so it's not a fixed value, but it is in the relation to a previous point. So when we are talking about the electric potential energy, is known as the difference of the potential energy, and it is known with the voltage. The name is voltage, and the symbol is V. So this is what we were talking. And now delta, like in every change that we are doing in every delta that we are saying, is the initial or the final minus initial minus VA. So is the electric potential energy at point B minus the electric potential energy at point A. Okay. The electric potential in a difference of the electric potential energy, so this delta V, is the change in the electric potential energy per unit of charge. So it is the change on the electric potential energy per unit of charge. In other words, the units for volts are joules, that is the unit for energy, over coulombs, that are the units for charge. And now, to honor the work that volts have done on this, we very often say that joules per coulomb is the same as volt. Now keep in mind what joules was. 1 joule is newtons times meters, or it is kilogram meter squared per second squared. And then this will be, volt will be either joules per coulombs or newtons times meters volt. Newtons times meters over coulombs, or kilograms meters squared per second squared times coulombs. Okay, so be aware of the different variation of the voltage, because even coulombs, joules has a different way to express it. Okay, so let's see now an example in which we are calculating the change of voltage. Let's suppose that we have, a charge that is I don't know, 1.220 times 10 to the power of negative 6 coulombs, and then in order to move this charge, we require an energy of let's say 4.20 times 10 to the power of negative 6 joules, sorry. And now we are moving this charge from point A to point B, and what we are looking for is what is the change of voltage. So the change of voltage between point A and point B that the charge is moving is delta E over, because it is the energy per unit of charge. So this will be 4.20 times 10 to the power of negative 6 joules over 1.20 times 10 to the power of negative 6 joules. And then the calculator will tell us that the change of voltage is 3.50 volts. Okay, so just keep this in mind when we are talking about the electric potential energy. Another thing that we need to keep in mind when we are working with the electric potential energy is that if you have a problem that they are not giving you what is the value of the charge, then you are in most of the cases you will use either the elementary charge, or you will see what is the multiples of the elementary charge that this charge has. So if we have a question like this, that the change of the energy, electric potential energy that needs to be applied into an electron, let's say, is 2.0 times 10 to the power of negative 918 joules, then what is the energy? What is the change of voltage that is implemented from moving the electron from point A to point B? So now, as you see here, the charge is not given, but since it is the charge of the electron, then we know that the charge of the electron is one elementary charge, and it is negative, but doesn't really matter in this case. And it is 1.60 times 10 to the power of negative 19 coulombs. So the change of voltage as the electron is moving from point A to point B, it is the change of energy, electric potential energy over the charge. So this will be 2.0 times 10 to the power of negative 18 joules over 1.60 times 10 to the power of negative 19 joules. And then in your calculator, the change of voltage will be 12.50 joules. Oh, sorry, volts. 12.50 volts. Okay. What do you have to keep in mind in terms of the electric potential difference? Is that it is a scalar quantity. Same as work, and we have dealt with it on Physics 20. Same as work, the energy and the potential difference between 2 points is a scalar quantity. So let's suppose that we have a question like this, in which we know what is the change of voltage. So let's say it is 150 volts, and we are looking to see what is the work done on a charge that is moving, a charge that is let's say 3.80 times 10 to the power of negative 5 coulombs. And the charge is moving against the field, the electric field. So this is kind of easy, because what we can say is that based on the work and energy principle, we can say that the change on the electric potential energy that the object is obtaining is equal to work. And on the other hand, the change of the electric potential energy is equal to the change of voltage times the charge. So this will be 3.80 times 10 to the power of -5 times 150. So the work done on the charge, which is equal to the change of the electric potential energy, will be, in your calculator, 5.70 times 10 to the power of -3 joules. And now this work is a positive work. And the same idea as we said when positive work done on the charge. Okay, so because it is moving against the field. Okay. I hope that this makes sense to you. Now, if we have an example in which we are looking now to what is the speed, like let's suppose that we have an example that we have an alpha particle, an alpha particle. So alpha particle that is moving in an electric field between 2 points A and B that has a difference of potential energy of 120 volts. If the alpha particle is released within the field, what is the maximum speed that the alpha particle will have? So meaning the fact that is released means that it is starting from an initial position, initial velocity of 0. Now, let's talk a bit about alpha particle. When you see alpha particle in your formula sheet, you will see alpha particle is like a sign with the letter alpha, and they will give you the mass and they will give you the charge. So mass of the alpha particle in your formula sheet will be 6.65 times 10 to the power of -27 kilograms. And the charge is saying that it is 2 plus or 2e plus, something like this. That means what you do have in terms of the charge is that it is double, because it is two times the elementary charge. Okay, so the charge of the alpha particle will be 2 times whatever is the elementary charge, 1.60 times 10 to the power of -19, or 3.20 times 10 to the power of -19 coulombs. And it is a positive one because alpha particle is a positive particle. Now, based on the conservation law of energy, what we have is that electric potential energy, that the change of the electric potential energy that the charge is undergoing is equal to the change of kinetic energy of the object. Now, on the other hand, we have an electric potential energy change here. Therefore, this will be whatever is the change of voltage times the charge of the object. And then the kinetic energy, on the other hand, is 1/2 mass of the object, change of the velocity to the power of 2. But since we are dealing with a released situation, then this will be 1/2 mass times V final of the object to the power of 2. From here, so now we have those two relationship. From here, we can isolate for the V final as the square root of 2 times the delta V times Q over mass of the object. So in our situation, what we will have will be 2 times, I think it was 120, yeah, 120 times 3.20 times 10 to the power of negative 19 over mass is 6.65 times 10 to the power of negative 27. And in your calculator, you will have, don't forget the square root. It's a very common mistake that students do. So final velocity will be 1.07 times 10 to the power of 5 meters per second. And yes, you will see those ranges of the speed. However, keep in mind, and this is a reminder for you, to not forget to square root, because the speed of any particles cannot exceed the speed of light, which is 3.0 times 10 to the power of 8 meters per second. Okay? So this is pretty much what is the electric potential energy of point source, and how do you deal with the difference of the potential energy between 2 points, and how do you make that relate that with the work and energy. So what do you need to know in terms of the Physics 30 curriculum is that you have to understand that what is happening with the electric field when it is moving against the field, or when it is moving within the field, and what is happening when we have the moving, in this case, in the case of the source, when we are moving in a circle, because those lines in which the electric potential energy is constant, doesn't change as the object moves from one point to the other on that line, that means that we are not changing the electric arm, and those lines are known as the equipotential lines. We'll talk more about this on the other video. Okay, that's it for this video.